Kubernetes and GKE Part 41. This episode has 8 questions. For each question, take a moment to think through your own answer before I share a strong approach. Question 1. Design a highly available Kubernetes cluster. Here's a strong way to approach it. A highly available Kubernetes cluster design in Kubernetes focuses on ensuring no single point of failure across control plane, worker nodes, networking, and storage, so workloads keep running even during failures. 1. Core design goal: keep the cluster operational even if a node, zone, or control plane component fails. This is achieved by multi-master control plane distributed at multi-node pools across zones, redundant networking, and load balancing. 2. High-level architecture global load balancer, API server LB ingress or LB, master 1, master 2, master 3, control plane, HA at cluster, 3 or 5 nodes, worker nodes, multi-zone node pools, app pods, replicated across zones. 3. Control plane HA design 3.1 multiple master nodes, minimum 3 control plane nodes spread across different availability zones. Components: Kuba API server, active, Kuba controller manager, leader election, Kuba scheduler, leader election. 3.2 API server load balancing: use external load balancer, AWS ELB or NGINX or HA proxy, routes traffic to healthy API servers. 3.3 at cluster, critical, 3 or 5 node quorum-based cluster must be odd number for quorum at quorum. 2 or 3 or 3 or 5 required data replication across masters. 3.4 high availability principle: if one master fails, cluster still works if 2 or 3 at nodes survive, cluster continues. 4. Worker node design 4.1 multi-node pools, separate node pools per workload type, front-end nodes, back-end nodes, system nodes. 4.2 multi-zone deployment nodes distributed across AZs, Zone A, Zone B, Zone C. 4.3 auto-scaling cluster, autoscaler adds or removes nodes dynamically, horizontal pod autoscaler, HPA scales workloads. 5. Application HA design 5.1 replicas use deployments, replicas. 3. 5.2 pod distribution use, pod anti-affinity topology, spread constraints ensures pods spread across nodes or zones. 5.3 health checks, liveness probes, readiness probes, startup probes. 6. Networking design 6.1 CNI plugin use production CNIs, Calico, BGP based, Cilium, EBP based. 6.2 service load balancing cluster IP for internal traffic, load balancer for external access, Kuba proxy or EBP based routing. 6.3 DNS HA core DNS deployed as multiple replicas, auto scaling enabled. 7. Ingress and traffic management use ingress controller, NGINX or ALB or Traffic. Deploy across multiple nodes, external load balancer in front. 8. Storage HA 8.1 distributed storage use cloud storage, EBS, GCEPD, Azure Disk, or distributed systems, Ceph, EFS. 8.2 persistent volumes, multi-AZ replicated storage, avoids single node storage. 9. Security and policy layer RBAC for access control network policies, Calico or Cilium. Pod security standards, admission controllers or OPA gatekeeper. 10. Observability stack, Prometheus, metrics, Grafana, dashboards, Loki or Elk, logs, Kuba state metrics, cluster state, metric server, auto scaling, Falco, runtime security. 11. Failure handling strategy, failure type solution, node failure, pod rescheduling, zone failure, multi-zone deployment, master failure, HA control plane at failure, quorum-based replication, app failure, HPA plus restart, network failure, multi-CNI redundancy. 12. Disaster recovery, DR backup at regularly, cross-region cluster replication, GitOps, Argo CD or Flux, Blue-Green or Canary deployments. 13. Example production setup. Real-world 3 control plane nodes, multi-AZ, 5 ET nodes, odd quorum, 10-100 worker nodes across zones, Cilium or Calico, CNI-NGINX ingress plus Cloud LB, Prometheus plus Grafana monitoring, Argo CD for deployments. 14. Simple analogy: think of Kubernetes cluster equals airline system control plane equals air traffic control towers, multiple redundant towers. Worker nodes equals airports, pods equals flights, ET equals central flight database, HA design equals ensures flights continue even if one tower or airport fails. 15. Key principles. Interview summary: a highly available Kubernetes cluster is designed by Running multi-master control plane using quorum-based cluster spreading worker nodes across multiple zones ensuring application replication. HPA plus replicas. Using robust networking. CNI plus DNSHA. Adding load balancers and ingress redundancy implementing monitoring plus automated recovery systems interview-ready definition. A highly available Kubernetes cluster is a distributed architecture of Kubernetes designed with redundant control plane nodes, quorum-based storage, multi-zone worker node pools, and resilient networking and storage layers to eliminate single points of failure and ensure continuous application availability during node, zone, or component failures. Nice. Let's continue. Question 2. How do you troubleshoot a Kubernetes pod stuck in crash loop? Back off. Here's a strong way to approach it. Start by checking kubectl describe pod for events, restart count, image pool issues, probes, resource limits, and node placement. Then inspect logs using kubectl logs previous because the current container may restart too quickly. Common causes include bad configuration, missing secrets, failed dependencies, insufficient memory, wrong command arguments, or failing startup checks. Great. Moving on. Question 3. A pod is running but the application is not reachable through the service. How would you debug it? Here's a strong way to approach it. Check whether the service selector matches the pod labels and confirm endpoints exist using kubectl get endpoints or kubectl get endpoints lists. Then test pod IP, service DNS, service port, target port, network policy, ingress rules, and application bind address. A frequent issue is the app listening on 127.0.0.1 instead of 0.0.0.0. Alright, next question. Question 4. How do readiness and liveness probes differ in Kubernetes? Here's a strong way to approach it. Readiness probes decide whether a pod should receive traffic, while liveness probes decide whether a container should be restarted. A failing readiness probe removes the pod from service endpoints without killing it. A failing liveness probe restarts the container, so it should only check unrecoverable application health. Let's keep going. Question 5. Scenario. After a deployment, 30% of requests fail. How would you respond? Here's a strong way to approach it. First, reduce impact by rolling back, pausing rollout, or shifting traffic away from the new version. Then compare old and new pods using logs, metrics, traces, config, environment variables, dependency versions, and request patterns. After identifying the cause, add better automated checks such as canary analysis, smoke tests, or stricter readiness probes before the next release. On to the next one. Question 6. What is the difference between a deployment, stateful set, and daemon set? Here's a strong way to approach it. A deployment manages stateless replicated applications and supports rolling updates. A stateful set provides stable network identity and stable persistent storage for stateful workloads such as databases. A daemon set ensures one pod runs on each selected node, commonly for logging agents, monitoring agents, CNI components, or security tools. Good. Here's another one. Question 7. How do you design resource requests and limits for production workloads? Here's a strong way to approach it. Set requests based on normal usage plus headroom so the scheduler can place pods reliably. Set limits carefully because CPU limits can throttle applications and memory limits can cause OOM kills. Use historical metrics, load tests, vertical pod autoscaler recommendations, and slow requirements to tune values over time. Nice. Let's continue. Question 8. Scenario. Kubernetes nodes are under memory pressure. What would you check? Here's a strong way to approach it. Check node conditions, pod memory usage, killed events, eviction thresholds, requests versus actual usage, and workloads without limits. Also inspect daemon set overhead, memory leaks, cache-heavy processes, and whether the cluster autoscaler can add nodes. Short-term mitigation may include scaling nodes or evicting non-critical workloads. Long-term fixes include right-sizing requests and improving workload memory behavior. Great. Moving on. That wraps up this episode. Nice work practicing, and see you in the next one.